Hi all. In this video, we are going to see one more application of Gauss law, that is when Gauss law is applied to a spherical shell, so how we can find electric field intensity at a particular point P. Now I am considering an imaginary sphere. I am considering an imaginary sphere of radius R, the imaginary sphere of radius A, so which has, see here, if you see this diagram, so here this imaginary sphere has a radius a, and this, on the outer surface of this imaginary sphere, the charges are uniformly distributed. The outer surface of this imaginary sphere, the charges are uniformly distributed. So I am considering here, I have to find what is the electric field intensity at the point P. So electric field intensity at the point P at three different positions. One position is when the point P lies outside of the sphere, and second case is when point P on the sphere, and third case is point P inside the sphere. So first consider the case 1 when point P is outside the shell. Then the radius of A will be less than the distance between center and the point P. So R, I will take the distance between center to the point P as R, and A is the radius of spherical shell, then the A will be less than R. So I will take this case as 1. So I have to find what is the electric field intensity at point P when the point P lies outside of the spherical uniformly charged spherical shell. So we know that the when I consider a point P outside of that, I have to consider a Gaussian surface including that point P. I have to consider a Gaussian surface including point P. So I will consider the spherical Gaussian surface. So as shown in this figure, I will consider spherical Gaussian surface with a radius of R. Now R is greater than A. The R is greater than A. Now we know that in a spherical surface, the electric flux density always directed radially outward. So always directed radially outward. So it is along the radius. So direction vector of D is AR cap. The direction vector of D is AR cap. Similarly, I am considering a surface area ds at point P, a small elemental surface area ds at point P. So which is normal to this radial axis, that is radius axis. So the unit vector normal to this elemental area is AR cap. So I can write in the surface normal to radius, I can write in a spherical coordinate system as ds is equal to r square sine theta d theta d phi. So in a spherical coordinate system, the elemental area perpendicular to radius line can be written as ds is equal to r square sine theta d theta. As I told, the flux outwards, radially outwards, in the direction of the radius. So electric flux density also in the direction of the radius. The direction vector of D is AR cap. Now we know that according to Gauss law, d psi can be written as d dot ds. So what is d? It is in the direction of radius. So I can write the radial component dr into direction component ar cap. So dot r square, that is ds, r square sine theta d theta d phi into ar cap. So if you simplify this, you will get dr r square sine theta d theta d phi ar dot ar cap will be equal to 1. So you will get this one. Now to get the what is the total flux lines, I have to integrate over the surface. So psi can be written as psi is equal to closed surface integration of dr r square sine theta d theta d phi. What will the limit for integration of theta will be from 0 to pi, and phi will be from 0 to 2 pi, because theta is half angle. So limit is from 0 to pi into sine theta d theta. If you integrate this and simplify this, you will get psi is equal to 4 pi r square dr. So you will get 4 pi r square dr. So but we know that according to Gauss law, you know that the total flux lines flowing from a Gaussian surface will be equal to total charge enclosed in that surface. So I can write then psi is equal to q. So psi is equal to q. So now I can write above equation in terms of q as q equal to 4 pi r square into dr. If I simplify that, I can write dr is equal to q by 4 pi r square. So dr means it is a scalar component in the direction of radial direction. So I can write the total electric flux density can be written as dr into ar cap. So dr is q by 4 pi r square into ar cap coulomb per meter square. Now how to find electric field intensity is using the relation between electric flux density and electric field intensity, that is E is equal to d by epsilon naught. So what is d? D is q by 4 pi r square. So if I divide by epsilon naught, I will get q by 4 pi epsilon naught r square into ar cap. Now we know that q in a surface charge density, I can write q is equal to rho s into surface area, right? So q is equal to rho s into surface area. What is the surface here? Surface is sphere. So what is the surface area of sphere? I can write surface area of sphere is 4 pi into radius square. What is the radius of this sphere? Radius of the sphere is a. So I can write rho s into 4 pi a square. So q is equal to rho s into 4 pi a square. Now substituting in this equation, so I can write E is equal to, instead of q, I will substitute rho s by 4 pi a square divided by 4 pi epsilon naught r square. This 4 pi get cancels. So I will get at the end, I will get E is equal to rho s a square divided by epsilon naught r square into a r cap. This is the expression for electric field intensity in a spherical shell when point lies outside of the spherical shell. So I can write expression for d as d is equal to epsilon naught e. E is rho s by a square into r square into epsilon naught. So epsilon naught get cancelled. So I will get at the finally I will get rho s into a square divided by r square into ar cap coulomb per meter square. This is the expression for electric flux density when the point lies outside of the spherical shell. Next case we will see when the point lies on the shell, when r equal to a, the radius of the sphere and radius of the Gaussian surface will be same. At that time, what is the expression for electric field intensity we will see. So we know that in the previous derivation we saw E is equal to q by 4 pi epsilon naught r square into ar cap. If you observe this equation, so E is equal to q by 4 pi epsilon naught r square into ar cap. We are using the same expression here. So same expression. So what is the r here? R is equal to a. So substitute in the place of r, substitute a, you will get E is equal to q by 4 pi epsilon naught a square into ar cap. This is the expression for electric field intensity when it lies on the shell, when the point lies on the shell. So this is the expression for electric field intensity in a spherical, uniformly charged spherical shell. In last case, we will see when point lies inside the shell. So then the radius of the Gaussian surface will be less than a. The radius of the Gaussian surface will be less than a. So this is your r sphere and this is a sphere. So the radius of this r is less than this a. So point lies on this sphere. So I have to find what is the electric field intensity at this point. As we know, the sphere is a uniformly surface charged one, not uniformly charged inside of the sphere. Only the outer surface of the sphere has charge q, but there is no charge inside the sphere. So I can write q is equal to d dot d s is equal to 0. But the area of the sphere can't be 0, right? So area of the sphere, we can't take it as 0 because area of a sphere is 4 pi a square. So it won't be equal to 0. So I can equate d is equal to 0. If d is 0, then q will be 0. So I can take d is equal to 0. If d is 0, then E is also equal to 0. So in case 3, the electric flux density or electric field intensity inside the sphere will be 0 when it is uniformly surface charged one. Okay, so when the uniformly surface charged sphere is there, the electric field intensity inside the sphere will be 0. To summarize this derivation, so for when the point lies inside the sphere, then electric field intensity is 0. When the point lies on the sphere, then E is equal to Q by 4 pi epsilon naught A square into AR cap. When the point lies outside the sphere, then expression for electric field intensity will be E is equal to Q by 4 pi epsilon naught into R square into AR cap. So if you draw this graph, the radius versus the electric field intensity versus radius, you will get graph like this. So when till R equal to A, that is the till here the point lies inside the sphere, so the electric field intensity is 0. At this time it will rise to peak value, that is Q by 4 pi epsilon naught A square. At this point the point lies on the sphere, so you will get maximum electric field intensity. As radius increases, Gaussian surface radius increases, so the electric field intensity on the point will be 0 because of the distance between the charged surface and the point will be maximum, so the electric field intensity starts to decrease. This is how electric field intensity varies when the radius of the Gaussian surface increases from 0 to the maximum value. So this is how in a the surface charged spherical shell, how electric field intensity varies with respect to radius of the Gaussian surface. So in next class we will see what is how electric field intensity varies in a uniformly charged sphere. Thank you.